Welcome to my review of stuff you need to know before you take a calculus class. We're going to go through a lot of things that you should have gathered from a pre-calculus class, whether you took pre-calculus or if you went through a trigonometry and college algebra class separately. Shouldn't really matter. It's all the same basic stuff. But coming into calculus, a lot of students still have gaps in their knowledge, and I'm hoping to give you the most important things that you're going to need to be able to do so that those gaps don't hold you back as you're studying calculus. All right, so starting from the very basics here, we're going to talk about functions. Now, if I were to define what it is, that's the most important aspect of college algebra. All right, so the very first part of a pre-calculus course. It is the study of functions. But what I often find is when I ask students what is a function, after they finished a college algebra class, after they get into calculus, after they finished calculus 2, if I ask them what is a function, they have no idea. Like they have no words for that definition. It's usually of the form like the best answers are like, oh well, it's like y equals 2x plus 5. That's a function. And okay, you've seen enough of these types of equations called functions that it is sort of an example of what a function could be. However, it's much more simple than that. It's much more basic. And as long as you understand what's happening at the most basic level in mathematics, it makes the more difficult stuff so much easier to understand. And those are the gaps that I'm trying to fill here. All right, so let's start with something a little bit simpler than a function. Let's start with a relation. So a relation is a correspondence between two sets of data. The elements of the first set are called the domain, and the elements of the second set are called the range. Now, it doesn't have to have an equation attached to it to be a mathematical relation. All we're saying is we have two different sets of data and they're somehow related to each other. So I like to demonstrate these with bubble charts. And you're looking at one right here. You've got one bubble chart, which is a set of data, which has 3 names. And then you have another bubble chart, which is a different set of data, which is a few different dates. And that's not the relation itself. The relation is how these items correspond to one another. So Mike here, if he corresponds somehow to the date August 1st, perhaps it's his birthday, or, who knows, all right? Doesn't really matter. He corresponds to that particular date. That correspondence is the relation. It's attaching Mike somehow to the data point August 1st. John, we could attach to June 16th, and Amy to May 5th. And now we've established a relation. The relation is the correspondence. That's the important thing to understand. Now, it's a one-way thing, all right? It doesn't necessarily mean that August 1st is just directly related to Mike in any particular way. It's a one-way relation here. So we have the domain, the starting point, is connected to the range, the ending point. Now, there might be a reverse relation. Doesn't really matter. Right now, all we're considering is one way. Okay? Now, a function is a particular kind of relation, so that every item in the domain corresponds to exactly one item in the range. I'm going to highlight that. So a function is a particular type of relation such that every item in the domain corresponds to exactly one item in the range. And I don't know why my highlighter's kind of lagging here. Doesn't really matter. So every item in the domain corresponds to exactly one item in the range. So, for instance, if I set up a relation between a set of names and some dates, I could say Mike is related to August 1st in some way. I could say that John is related to August 1st in some way. Amy is June 16th and Doug is May 5th. All right, so that's fine. This is a type of function. So it's always a relation because you have two sets of data the items in the first set are somehow correspond to the items in the second set. All right, but this is also a function. So this is a relation and a function, because every item in the first set corresponds to exactly one item in the second set. And it doesn't really matter that John and Mike here correspond to the same date over in the second set. That's fine. It just, each item in the domain has to correspond to exactly one item in the range. All right, let's go over to this next example. So here we have two names, Mike and John. And if I say Mike is somehow connected to August 1st, and then John is connected to June 16th and May 5th. This is still a relation because it's a set of data corresponding to some other set of data, but a relation is a very general correspondence. A function is very specific. The function says that each item in the domain can correspond to only one item in the range. John here corresponds to two items in the range. So it's a relation, but not a function. All right, now, that's really it. That's when it comes down to functions, like that's all there is to it. Now, you definitely would have some prior experience with the concept of functions through equations like what we mentioned earlier, y equals 2x plus 5. Okay, so let's kind of bring it back into that sort of idea, but we're going to take baby steps here. All right, the first thing that I really want you to understand is that a function needn't have an equation like that attached to it. It can simply be a set of points. So for instance, this set of points right here is enough to define some function. All right, as long as it doesn't violate the principle that each item in the domain has to correspond to exactly one item in the range. All right, how do we define the domain in the range? Well, okay, so we have for each coordinate, we have an xy coordinate pair. And that xy coordinate pair defines two different pieces of data. You have a piece of data that comes first, and that comes from the domain of your function. Then you have a piece of data that comes next, which defines the range of your function. Now, it's not just each individual data coordinate pair that's doing this. It's all of them together. So, like the domain, there would be this bubble chart, for instance. The domain would have the values 0, all right, 1, 3, and then we have 1 again. But we wouldn't list the 1 the second time here, all right? I wouldn't put 1 in here another time, because if you remember just the littlest parts of set theory, you don't have any repeated items within a set, so you wouldn't write the 1 a second time there. All right, now, if you go through the items in the y, so let me label this x and this y. You have a 2, all right, but this 0 corresponds to this 2. All right, then you have a 4 in the y, but this 1 in the x corresponds to that 4. Then you have another 2, all right, but the 3 corresponds to the 2. Now you don't put another 2 in here, you simply just reconnect the 3 up to the 2 that already exists. Because again, set theory says don't repeat values. Then you have 1, 1. All right, so then we have this right here. So this is really what our relation looks like. All right, so again, it is a relation, but the question is it a function? Well, let's see here. I have this one data value right here at 1, which is corresponding to 2 different values over here in the range. And so therefore it's not a function. Now, I want to keep bringing this up into higher levels where you probably meet some of the things that you already know about mathematics. Like for instance, the vertical line test. Sometimes I'll have a student, when I ask about, what is a function? Sometimes a student will answer, "Oh, well, it's something that passes a vertical line test," and that's actually a really good answer, because it's a relation that has to also pass a vertical line test, given if we're talking about xy coordinates. So, for instance, if we are talking about xy coordinates, so we have two axes, x and y, and they're labeled here. I'll just mark off by ones. Same thing on the x and the y axis, and plot these points. So like 0, 2. So 0, 2, that point is there. 1, 4, that point is right there. 3, 2, that point would be right there. And then finally 1, 1, that point would be right there. And the problem is, these 2 points lie on the same vertical line. So what that does is it tells us that it fails the vertical line test. And if a group of points that are graphed on an xy plane fail the vertical line test, it's not a function. All right, and there's also, along with a vertical line test, there's also a horizontal line test. The horizontal line test says that if 2 points lie on the same horizontal line, like for instance these 2 right here, it doesn't say the horizontal line test whether it's a function or not. Okay, it still can be a function, but if it fails the horizontal line test, we say that it's not one-to-one. And you may have heard that terminology in previous courses about a function being one-to-one or not one-to-one. All right, if you haven't, we'll discuss it a little bit further, a little bit later when we get into inverses. But for right now, this is, a separate idea from it being a function. So the vertical line test tells us if a graph represents a function, and the horizontal line test tells us if a function is one-to-one or not. All right. So let's take a look at a couple of quick examples here. So if I wanted to check the vertical line test for A, I just need to draw a vertical line so that it intersects the curve. I'm using the term curve lightly here because a curve could be a straight line in terms of mathematics. If it intersects the curve at more than one point, then it fails the vertical line test. But this one only intersects at 1, no matter where I draw that vertical line. So it passes the vertical line test. Therefore, it's a function. All right, now the thing is, if we look at the horizontal line test, it would only ever cross at a single point as well, so it passes the horizontal line test. So it's one-to-one. So we would say that this particular graph is a one-to-one function. And that's pretty easy to recognize. Like, there's not much to that, so it's just a little bit of understanding. But it's an important concept because it tells us a lot about what we can do with this particular set of points. All right, so this next one. Anywhere I draw a vertical line would only cross the graph in a single point, so it passes the vertical line test. If I draw a horizontal line, pretty much everywhere, I end up touching the curve at more than one point, so it actually fails the horizontal line test. So it is a function, but not one-to-one. So let's write it this way. A function, but not one-to-one. Okay, C, I'm going to start speeding this up here. All right, drawing a vertical line, it's going to touch at multiple places, so it's going to fail the vertical line test, which means it's not a function. And here's the thing, it doesn't really matter if it's one-to-one if it's not a function for most purposes. So at that point, there's no real reason to do a horizontal line test as well. it would technically pass it, but if it's not a function, for what we're concerned with, it doesn't really matter if it's one-to-one or not. We're only really concerned with functions at this level of mathematics. That's why it's so important to have a good working definition of this stuff. All right, so if it's not a function, we just move on. Next up, then any place I draw a vertical line here, it would pass a vertical line test, but it would fail a horizontal line test. So this would be a function, but not one-to-one. All right, the next one, it would certainly fail a horizontal line test. All right, and then therefore there's no real reason to actually look into the horizontal line test because it doesn't really matter if it's one-to-one. Technically it would be, but it doesn't really matter. Lastly, if we look at a vertical line here, this one's a little bit weird. This is called a piecewise defined function. And you might even want to test at different places. Like here, it would only touch the graph at a single place. It might look like things are happening weirdly here, but this open circle says it's not really defined up at this point, but it is defined down here. So it is only defined at a single place. So it still works. It still is just fine. All right. As long as both of these places weren't closed circles, everything's fine. Like it's not being defined at two different places. This is, in this case, only defined once. So this actually passes the vertical line test, but it certainly fails a horizontal line test because you just need to find one horizontal line where it doesn't, where it crosses the graph more than once. So this would be a function, but not one-to-one. All right, so enough about that. Let's talk about domain and range. All right, so looking into domain and range. So domain is a set of numbers. You can think of those bubble charts. Generally speaking, for equations that we're working with, it's an infinite set. All right, it's an unimaginably large infinite set, which is why it's better to use like a equation to represent the concept of what numbers are corresponding rather than bubble charts. All right, because this is an infinitely large set, it's not very good to try and like list out the values. So instead of listing out the values that are possible, we often use interval notation. And interval notation allows us to express ideas of a whole bunch of numbers in a row just by indicating the starting point and the ending point. And then it just kind of assumes that all the values between those are included. I'll show you some examples in a moment. The range is the set of all the y values that happen to have some corresponding x values. So it's the same thing as these bubble charts, but we can't have any repeated values. And that's kind of the idea that we're trying to not contain. All right, so for instance, the domain and range of these following graphs here. All right, so the domain. If I were to try and make bubble charts here, I would be trying to identify all the different x values that have some corresponding y value over here in the range. So if I'm looking at all the coordinates that make up this graph, I'm trying to make pretty much like a list of those. But here's the thing, like this one's at maybe -9. This one I sort of put it looks like, I don't know, -7.8 or something like that. It's not exactly at -8. You would think the next value after -9 would be -8, but not really. There's a whole bunch, there's an infinite number of values between -9 and -8. You can't really just list them all. You can do kind of things like, you know, let's say we want to include -9, -8, all the way up to, say, +9, something like that. But that pattern sort of looks like you're only talking about the integers alone. It doesn't really say that you really mean like all the values in between. All right, so in order to do this, we want to use interval notation instead, because if I write an interval, like say starting with -9 and going up to +9, The brackets mean that I'm including the endpoints, and every single number that's possible between -9 and +9. It doesn't matter how many decimal places it has, or if it can be represented as a fraction or an integer. It's every single possible number within those values. So it's much more convenient than trying to list out an infinite number of potential items. So we use this interval notation. Now, the interval notation can get a little bit tricky sometimes, because here's the thing. Like, for every single point that I find along here, I'm trying to find out if in the x there is a corresponding y value. So for, say, -9, there is a corresponding y value here. For -6, there is a corresponding y value. So for different values on the x, there are corresponding values in the y. And because this is a continuous line, all these numbers in between are also considered as well. All right, so I'm off on a tangent here, but what I want you to understand is the reason why we write this stuff in interval notation. So practically every single number along the x-axis has a value that's corresponding in the y. It's actually, you can't find a single value on the x that doesn't correspond in the y. So my domain here is all the numbers. So it's every single number from -infinity up to +infinity. And the range is similar. It's every single number is represented. It's -infinity to +infinity. Now, one thing that I ask students to do is sort of try and imagine like the image of the graph onto the x-axis. That's going to be your domain. Or the image of the graph onto the y-axis. That's going to be your range. Let me show you what I mean by the image of the graph there. All right, so here's our graph. Now, what I mean by the image of the graph onto the x-axis is kind of like, if you think of, like, you know, everything in the y, if it just gets smashed up against the x-axis like this. So this is kind of like a trash compactor, you know, like in Star Wars, when everybody's like stuck in that trash compactor and the walls are caving in on both sides. Eventually it's going to squash everything into one axis. And so that's kind of what's happening here. If I squash everything into just the x-axis, the remaining set along that x-axis is the domain, which is all real numbers here. If I do the same thing along the y-axis, then what's going to happen is it's going to leave me with the set of values that is considered the range, so all the possible values that could happen from that particular graph, which is all real numbers. All right, let's go on to the next example. All right, so now I have y equals x minus 3 quantity squared minus 5, which I've already graphed for you. See, the domain here, if we think about it in the same way, it's the image of the graph when I smash it up against the x-axis. So all of these points here have some image onto the x-axis. Now, it might look like it's sort of restricted here from, say, like -1.8 to 6.4 or something like that. Who knows? But the thing is, like, this graph is just increasing so rapidly, we don't really see it continuing on to infinity. All right, it continues in the same pattern. So even though it looks like it kind of stops between two values, if I put in, let's say if I put in 8, 8 doesn't have a corresponding value here in the window of this graph, so what we're actually just seeing. But if I put 8 into this function, 8 minus 3 is going to be 5. 5 squared is 25. 25 minus 5 is 20. It has a mapping. It goes to the value 20. It's just the scale only goes up to 10, so we're not seeing where it is at 20. That's fine. It exists. The domain here is -infinity up to +infinity. The range, however, let me erase some of these markings here. The range is a little bit different. So the thing is, If I pick any value along the y-axis, say like positive 2, there is a corresponding value in the x. Like eventually I run into the graph. If I choose negative 4, that's fine. I run into the graph. That's part of the range. But if I choose negative 8, there's no corresponding values of the graph anywhere at negative 8. So that's not part of the range. In fact, the range starts about right here and goes up this way, and that's all we have really. So the range is really like, in this particular case, negative 5 up to positive infinity. All right, and this set, the reason I wrote it the way I did, you go from the smaller value to the larger value. Negative 5 is the smaller value. Positive infinity is the larger of the two values. So it's all the values in between there. All right, let's look at this graphically. Okay, so here I have the same graph that we were working with just a second ago. X minus 3 quantity squared minus 5. If I squash the domain up against the x-axis, all right, then what happens is all the points are filled in from what we could basically see. So from like negative 1.2 up to 7.2. But like I said, these values extend beyond. All right, so this actually still is negative infinity to positive infinity. All right, the range, if I squash everything up against the y-axis, the range here you kind of really do see. It's just the values from negative 5 up to positive infinity. None of the values below negative 5 have any corresponding value to them. So that's the range and how it's determined. Okay, now that we've done a couple of examples, I'm going to speed things up for the next couple here. The next one is a type of a rational function. And rational functions often will have horizontal asymptotes and vertical asymptotes, which you should know a little bit about. Vertical asymptotes are places where we run into division by 0. So if you take x minus 2 and set that equal to 0 and solve, you end up with x equals 2. So that means there is a vertical asymptote at x equals 2. And that vertical asymptote, even though I didn't draw it in, just kind of looks like this. It's a place where the function is undefined. So that's not part of the domain of the graph. So the domain here, if I smashed everything up against the x-axis, it would be all real numbers from negative infinity up to 2, but it doesn't include 2, and then from 2 to positive infinity. All right, details here. First, the U tells you to join two sets together. It means union. You don't separate them with commas to join them. You just use the symbol U. And then the parentheses. Parentheses mean exclusion. And whereas up here, I used a bracket, which represents inclusion. All right, inclusion is kind of like the idea of a closed circle. Exclusion is the idea of an open circle. All right, so if you want to exclude a point, you use parentheses. If you want to include it, you use brackets. Now, there's also a horizontal asymptote, and this horizontal asymptote is right through here, which looks like it's at negative 1. So the horizontal asymptote is a place where the function is not defined, in the range, that is. So this goes from negative infinity up to negative 1, and then from negative 1 to positive infinity. All right, so that's that. Moving on to the next one, this is a function that is purposefully on a restricted domain. Restricting domains is a really important concept in application problems, because sometimes it just doesn't make sense to use values, say, that are negative if they're supposed to represent like lengths or velocity or something like that. Oh, I guess velocity could be negative. Sorry, bad example. But in general, like physics examples, you have negative numbers not really considered. Regardless, you can have restricted domains for different reasons. If you have a restricted domain, it actually makes it a little bit easier to determine what the domain and range are. So for instance, if you're on a restricted domain, well, as long as you have a continuous curve between the start and end point, your domain is the restricted domain. That's why we call it a domain. And of course, that would be a closed circle there. It starts at -2, and actually that would be an open circle. And then it ends at +5, and everything exists between those 2 points if we were to smash that graph up against the x-axis. If we did the same thing for the y-axis, so if I took all the points from here, which is at -4, up to here, which is at +5, then all the points in between make up the range, and that was supposed to be an open circle. I didn't really do a very good job there, but -4 to +5 is my range. All right, so that's how we would do it on a restricted domain. Okay, now operations on functions. So if you think about the concept of bubble charts, it should make perfect sense that you can do any operations that you want on functions. It may seem kind of weird that, for instance, if I want to do like f of x times g of x, if I have some definitions like this. So like f of x times g of x, it should make sense that you would be doing x plus 4 times 2x minus 1. And if you were to evaluate that, then what would happen is x times 2x would be 2x squared, x times -1 would be -x, so then plus 8x and minus 4, so I'm just expanding using FOIL. So I get 2x squared plus 7x minus 4. So the thing is, I think students kind of miss what actually happens there. So let's really look at the details. All right, if I were to take that function f of x, which is we're using x plus 4, and evaluate it at a couple of different places. So if I evaluate this at -3, so -3 plus 4 is 1. 2 plus 4 is 6. 5 plus 4 is 9. So these are the some domain values, and these are the corresponding range values. All right, let's go on over to g of x, which was 2x minus 1. Hopefully I don't make an arithmetic mistake as I go along. 2 times -3 is -6, minus 1 is -7. 2 times 2 is 4, minus 1 is 3. 5 times 2 is 10, minus 1 is 9. Okay, now the product, f of x times g of x, so that's that function 2x squared plus 7x minus 4. Okay, so if I were to evaluate this, I'm actually going to grab a calculator just to make sure I'm not making any arithmetic errors as I go along here. All right, so all right, and because I have to evaluate a function at a few different places, I'm going to use a little bit of an advanced feature of the calculator called a table. And it just allows me to evaluate a function at multiple places. Set up my table, that looks good. And I can just type in where I want to evaluate that function that I put into y1. So if I want to evaluate it at -3, all right, it comes out to -7. If I want to evaluate it at 2, that's 18. And then if I want to evaluate it at 5, I get 81. All right, so -7, 18, and 81. Okay, now here's the thing I want you to see about these particular numbers. Now, these came from this particular function right here, which was the product of these two functions. Now, look here, the value -7. If I took the product of -7 and 1, the individual values of f of x and g of x, that multiplies to -7. Okay, well, maybe not that impressive because like 1 times anything is itself. But if I did 6 times 3, you have to admit that would be 18. And if I did 9 times 9, that product is 81. So if you'll notice, I could do this in one of two ways. I could either find the product function like this, and that would get me directly to these values over here, or I could find the individual values of f of x and g of x, which are these numbers right here, and I could multiply those together, and I would end up at the exact same results. So the point is, a function is just a correspondence or a mapping between x and y values. So the function is not the x plus 4. X plus 4 tells me how to get from the values in the x to the values in the y. It's just telling me how to get there. It's not the function itself. Now, I know I will call it a function throughout the class, but it's not technically the function. The function is the mapping between the points. And so this f of x really is just a set of y values here, okay? So it's just a single number. X plus 4 is a single number. 2x minus 1, it's a single number. And that might seem weird to you at first because you see the 2 and you see the negative 1 and you know that x represents a value and you might be saying, that's 3 numbers, Mr. Flinner. But in the end, once you take x and plug it in for x, you can evaluate it down to one single number. So it is just that single number that is the g of x value. And so all you're doing when you're taking the product f of x times g of x is just multiplying two numbers, which should make perfect sense why they will always end up being the product of the two functions individually. All right, so that works with multiplication, addition, subtraction, any operations that we do on functions at all. So there's one special type of operation on functions that's a little bit different, however, and it's extremely powerful. I hope at some point through the class I am able to show you the true power of function composition, because a lot of students overlook it. They look at it and they're like, nope, I don't want to do that. That seems terrible. But honestly, it's there to take like really complicated ideas, make them simpler to understand so that you can work on simpler ideas and then bring in more complicated things later on. It's for simplicity. It's a function operation that allows us to evaluate a function at another function, okay? And that might sound a little bit strange, but I'm going to show you some examples and hopefully you'll understand here. But at its very basic, right back up here, when I evaluated f of negative 3, I did a function composition. It's just this is a constant function, and I'm evaluating f at a constant function negative 3, and when I do that, it happens to evaluate to a single number. So 3 plus 4 is positive 1. So, but I did function composition. If you can do that, you can do all of the other types of function composition, which doesn't involve numbers, and that's when students usually get a little bit tripped up. Now, the notation here, this little open circle looking thing here, is what we use for function composition. Don't mistake it for multiplication. If it were multiplication, I would use a dot, or I wouldn't put anything at all between them, right? Now, the open circle means composition. It tells me to take the function f of x and evaluate it at the function g of x. All right, so here's the thing. I'll leave f alone for a second. G is the function x squared plus 16. So what I'm doing is I'm evaluating the function f at x squared plus 16. And you can just think of this portion of a function as like a magic box if you want. And you have this mapping. This 2x plus 1 is a mapping, and it tells you to take 2 times whatever's in that magic box plus 1. Now, it is sort of helpful to think of anything in that magic box is surrounded by parentheses, and that way you won't mess up with parentheses, order of operations, that sort of thing. But since I put x squared plus 16 inside here, in that magic box, it just shows up over on this side. Every x that you have gets replaced with whatever you put inside these parentheses. So this would be 2x squared, after I distribute the 2, plus 32 plus 1, so 2x squared plus 33. And that's the composure between those two functions. All right, now composition doesn't work the same both ways very often. And so you have to be careful which way you're plugging in the values. So if I wanted to do g of f of x, that would be different. G of f of x is to take the function g and evaluate it at f of x. F of x is the 2x plus 1. Okay, so g of x is whatever I put in that magic box squared minus 16. Okay, so I put in that magic box 2x plus 1. And again, always put parentheses around these things. Okay, and then algebraically reduce it. It probably isn't going to end up with just a number. It's probably going to be some other function. That's fine. Okay, this would be multiplying out here. This would be 4x squared. 2 times the first would be 2x times the second one 1, so that would be plus 4x. Sorry, I said 2x. 2 times 2 is, of course, 4. Plus 1 minus 16. So 4x squared plus 4x minus 15. And if you're not sure how I multiplied that, start foiling. All right, FOIL is the basics of all binomial expansions. All right, let's look at something that is a good application of the power of the function composition. So I have this expression which just looks daunting. Okay, now the thing is, function composition can really make this a whole lot easier to work with. So for instance, if you'll notice, there's kind of these like repeated parts which look very similar. So I have a lot of different parts with t squareds plus 1s. Okay, so if I just let, say, I don't know, a be equal to t squared plus 1, this is a form of function composition. It's allowing me to substitute something that's complicated for something that's easier. So this would be 2 times t times the square root of a plus t cubed times a to the negative 1/2 all over a. And so the idea is I've got just something a little bit simpler to look at to start with. And I'm not going to go through and simplify this fully. I don't know if we're ready for exactly that just yet. But I just want you to think about function composition's purpose is that we take something that looks scary, possibly just make a quick substitution to make it look less scary so that we can then proceed on with something that we do know, we can get started in the problem, and then work, from there. All right. So anyway, let's look at graphs. All right, so graphs of functions are very important. And after we get through graphs, we'll have concluded the first portion of these review videos, which is, I think, probably going to be the longest of them, except maybe for the trig. All right, so graphs of basic functions. These graphs that I've listed here, you should just know what these graphs look like. Our basic elementary functions, we have the linear function, the quadratic, which is the squaring function, cubic, the reciprocal, square root, cube root, absolute value, exponential, and logarithmic functions. These are all of our basic functions, not including the trig functions. I'll give you graphs of those when we get to trig stuff. You should know every single one of these graphs. You should be able to see a square function and picture in your mind there's going to be a parabolic relationship. Okay? If you see a reciprocal function, you're going to know that there's the potential for division by 0, so you could have vertical asymptotes wherever you have division by 0, and then horizontal asymptotes could exist as well. We'll talk about when we get to rational functions in general. Exponential and logarithmic functions also have horizontal and vertical asymptotes, and they have special points that they pass through. You should know all these different aspects. all right, because it will make your life a whole lot easier to not have to grab a calculator every single time that you need to graph a quadratic function. You should be able to graph most quadratic functions without a calculator pretty easily, especially if they're in the form y equals ax squared, or a times x minus h squared plus k, because these are our basic transformations of functions. And using basic transformations, we can pretty well predict what the graph of a function is going to look like without having to get a calculator to prove it. All right, so first off, we have a stretch or shrink factor, and that's the value a. It's on the outside of the function. It just determines like how wide a parabola is or how skinny a parabola is. Right, I'll show you how to do that in a second. H is a horizontal shift. It just moves our graph to the left or right. And K is a vertical shift. It just moves the graph up or down. And it doesn't matter what type of function we're working with. All of these functions work the same way. So let me show you a quick little applet that's going to help you really visualize and understand that. Okay, so here is our basic quadratic function. All right, y equals x squared. This is what the graph originally looks like. Now, if I were to affect the value h, so over here I'm going to change the value of h. So if I change h to 1, and I have the graph of x minus 1 quantity squared, so the h is on the inside of the function, okay? All it does is it moves the graph 1 unit to the right. Now notice it says x minus 1, which you might think that it would go to the left. Horizontal transformations go in the opposite direction of their sign. All right, just something you'll have to make sure you contend with. All right, but whatever you set h to, all it does is just moves the graph left or right that many positions. It doesn't change the shape. It doesn't have any other effect. It just moves everything that many units. Similarly, k, it's the value on the outside of the function. So notice here x minus 2 quantity squared plus 2. It just moved all the points up 2 units. All right. If it's negative 2, it just moves all the points down 2 units. And so everything just kind of moves in the same fluid manner. So you kind of start with a known point, which is usually the origin. And if it's x minus 2, that's a horizontal shift to the right 2 units. All right. And then if it's, oh, that's off for some reason. There we go. And if it's minus 2 on the outside, if k is negative 2, then it's down 2. So then you come down 2 units from that particular point. And that gives you basically the new vertex, which is the new origin point of the graph. And then you can just draw the exact same graph from there. Now the more difficult one is the stretch factor. All right, so a. But if I multiply some, a, if I change that value of a, just say like 2, this actually can be very predictable as well. Starting from this vertex point, if you go 1 unit to the right and up whatever a is, that gives you the next point on the graph. So here a is 2, so you go up 2 units, and it tells you where the next point is. All right, if it's negative 2, if I can get it to land right on negative 2. All right, so you find your vertex point. Go to the right 1, down 2. That gives you the next point. So it's actually pretty predictable, but that only works from the vertex point 1 unit away. All right, so let me bring it back upward. All right, so if I go like 2 units over, I actually have to go a lot further up to reach the next point. So it's only 1 unit to the right and up. Or you can do the opposite and go 1 unit left and up, but I generally just say go 1 unit to the right and then use symmetry of the graph to figure out the other points. All right, so that's how we do that. Cubic graphs work in the same way. So as long as you start with your, oh, there we go. That's what I meant to do. Start with the origin. Okay, whatever horizontal shifts are applied, it just moves the graph left and right, whatever number of units. Vertical shifts work in the exact same way. And then those changes to A, they work in the same way as well. So like from the vertex, the original place where the origin was, if you go to the right one and up whatever A is, that gives you the next point on the graph. So all of these graphs work in the exact same fashion. You just need to know the basic shape and how these transformations affect the graph. And that allows you to really graph a bunch of these in the exact same form, same way. Exponential and logarithmic, they have a few key differences of themselves, but I'm going to go into exponential and logarithmic graphs later on when I talk about those types of functions. So let's just focus on some of these original ones here first, but I'll do a quick example with one of them. So just to give you a preview. All right, so know all these different shapes. All right, so let's look at how we can graph some things. All right, 4 minus absolute value of x plus 1. This is a horizontal shift. And I need to go to the left 1 unit. All right, because it goes in the opposite direction of the sign. So normally, this graph is going to, of course, just be this V shape. All right, but I'm going to go to the left 1, so that gets me started. This outside here, this is a vertical shift, and it's going to be up 4 units. All right, so 1, 2, 3, 4. And then this negative on the outside of my function, it flips it. So what it does is it points everything downward. So that means my graph looks basically like that. Okay? You can grab your calculator to check, but that's pretty much how it works. All right, next one here, x minus 2 quantity squared plus 3. So we start normally at the origin here and have this parabolic shape, but we have a horizontal shift, which is going to go to the right by 2. So that's going to go over here. And then this is a vertical shift, which is going to go up 3. So up 1, 2, 3. And then the multiplier here is 1. So if you go to the right 1 and up 1, that gives you the next point. And then the parabola is just symmetric. And I didn't really make it all that symmetric, but it should just kind of look symmetric at that point. There you go. That's a great one. All right, this one's an exponential. The only thing that's different about exponentials and logarithms is that they don't pass through the origin. Okay, but the thing is, we have this horizontal asymptote which goes through the origin. So you kind of start moving the horizontal and vertical asymptotes, and then you work with this point which is known. And for exponential functions, it's always 1 unit above the asymptote, and it's 1 unit in front of the asymptote for logarithms. All right, so anyway, this is how we would do this. So this is a vertical shift going down 1 unit. And if I have a vertical shift going down 1 unit, then I move that asymptote down 1. That's the easiest thing to start with. This is a horizontal shift, which is moving everything to the left by 2. So normally I would have this point, which is 1 unit on just right above the asymptote on the y-axis. But it's going to the left too, so it's going to be over here instead. So the shape of the exponential, it kind of grows very slowly up to this point, and then it sort of turns and grows very rapidly. And that's perfectly fine. The base does have an effect on the graph, which I'll show you later, but it's a little bit more difficult to really draw that in accurately anyway. So for the most part, just kind of draw in the shape and you're fine. And actually, you know what? I'll just show you real quick the effect of that. So of the base, let me get rid of this multiplier. Multiplier 1. That's hard to do, sorry. All right, and let me make the base 2. So what happens is, if the base is 2, the original graph before I do any shifts left and right. If you 1 unit above the asymptote is where that original point's supposed to be. If you go to the right one and then up 1 less than your base, that's going to be the next point. So for instance, if I make this 3 instead. Oh, wrong value, sorry. This one's the base, so I changed the base to 3. All right, so if I change the base to 3, did it? Oh, okay, it did. All right, so this point got moved over to here because this one has a transformation 2 units down, 3 units to the right, and then that's where this point maps to. All right, that's our starting point. You go to the right one and up 2, which is 1 less than the base, that takes you to the next point. Again, exponentials, not so important to really be able to get all those details worked out. As long as you have the basic understanding of the other functions, that's great. All right, so when you have a good working understanding of the other functions, you can do things like this. You can go in reverse. You can find a function that's going to produce a graph. So for instance, if you'll notice here, this is the cubic graph. All right, so there's going to be like y equals something times x minus h cubed plus k. H is the horizontal shift. So we're going over here to the right by 3. So this would be y equals something times x minus 3 cubed. And if you'll notice, it also goes down 1, so k is negative 1, so minus 1. And then a, if you'll notice here, if you go to the right one and then up 1, that's going to tell you what a is. A is just 1 in this case. So that gives you a function which produces this graph. You should be able to do that sort of thing, if you know these graphs well enough. All right, last in this part, restricted domains. So sometimes you may not want to draw an entire graph. You might want to just draw parts of it. That's called a restricted domain. And these are the basis of piecewise defined functions. And I know that piecewise defined functions were things that were stumbling blocks for students in algebra. But the thing is here, they're very important when it comes to determining limits in calculus. All right, so you really need to have a good understanding of piecewise defined functions. There's not really much to restricted domains, however. So if I want to graph, this is the simplest case I could come up with. Y equals 2, which is a horizontal line. So you're seeing that horizontal line right here. It's just a horizontal line at y equals 2. All right, on the domain from -3 to infinity. So in orange here, you're seeing the domain. So this is -3, and this is going off to positive infinity. So what I'm saying is the only place where this function is defined is subject to these particular points. So the actual graph of this thing is this graph right here. So you can't really see it all that well in blue because the black line, but let me shade it in a little bit so you can see it a little bit better. So this is my graph. That's the graph subject to that restricted domain. It just ignores these points back here, which are off the domain. That's all. This next one, -4/5 x plus 2 on the domain from -2 to 4. -2 is included, sorry, and 4 is excluded. I had that backwards. Anyway, so here's the restricted domain at -2, and then here's +4. So that's the restricted domain. Now, the thing is, we only want the part of this line subject to that domain. So that means wherever this point maps to is kind of our starting. Wherever this point maps to is our ending. So it's just this portion of the graph right through here. So you just consider the parts on the restricted domain. All right, let's do one without a starting graph. Okay, so -x minus 1 on the restricted domain from negative infinity to 2. Now, this is a linear graph. You should absolutely know how to graph that. We have a y-intercept of -1 and a slope of -1. All right, so that's pretty much what this graph looks like right there. So you should be able to do that comfortably. Now the thing is, we are restricting it to the domain negative infinity to 2. So here's negative infinity, and here's 2. So we're just restricting it to this portion of the domain. So it's really just this part of the graph that really matters to us. The rest of it is gone. So in effect, all we want, whoops, sorry, let me try that a little bit better, is this graph right here. So that is ultimately the graph that I'm looking for. Okay, which brings us to piecewise defined functions, because here we can have multiple functions on restricted domains as long as those domains don't overlap. So like for instance, negative 2x plus 3 on the domain where x is less than 0. So x is less than 0 over here. It's greater than 0 on this side of the y-axis. So all these values have x is less than 0. All these values have x is greater than 0. Okay? So I have the function negative 2x plus 3 where it's less than 0. So negative 2x plus 3, that has a y-intercept of 3 and a slope of negative 2. So if I go down to back 1, down to back 1, all right, so that is the graph of, oh, I did that backwards, sorry. That's a positive slope. So it's a negative slope, so I went in the wrong direction. So rise over run. So rise over run would, of course, be a rise of, so like a rise of negative 2, which would be down 2, and then a run of 1, all right? Which will put me over here, which is actually outside of that domain. You can reverse this, and that's what I was trying to do in my head, and I did it backwards, I'm sorry. So you can think of this rise over run as negative 2 over 1, or as, 2 over negative 1, which means you go up 2 and back 1. And that gives you a couple of points that exist over here on this side of the line, which is what we want. All right, the other part's actually easier. It's a straight line, y equals 2, it's a constant, where x is greater than or equal to 0. So x is at 2 the whole time, or we're greater than or equal to 0. So that's that's the function subject to that restricted domain there. And so you don't necessarily have to be able to graph piecewise defined functions for this class, but you have to have a formal understanding of how to pretty much evaluate them. So if you needed to evaluate, say, f of 4, all right, so you would know that 4, 1, 2, 3, 4 is on this domain. So you're using the function here because it's on this domain. So the result would be 2. Or f of, say, negative 2. F of negative 2, so negative 2 is back here on this domain, so you would use the line negative 2x plus 3. So negative 2 times negative 2 plus 3 would be 7. All right, so you would need to be able to do those sorts of things for this particular class. Okay, but understanding how the restricted domains work is the key to starting that.